Okay, here's part 2 of the ideal gas law. It's for the honors and the AP. Now, okay, so problem C says, okay, 2 grams of nitrogen gas at 25 degrees Celsius and 3 atmospheres are contained in a compressed steel cylinder. More nitrogen gas is added inside the cylinder, and the pressure increases from 5 atmospheres and the temperature increases to 27 degrees Celsius. After adding the gas, what was the total number of moles of nitrogen gas inside the cylinder? Okay, now let me just tell you this, because I know if you go through, actually, before you watch this part of the video, you might want to do the problems that are on the worksheet that are in the part 1. They just do PV and RT, the first few problems that I assigned you. I think there's 2 of them assigned. I don't have the worksheet in front of me. But then in the next, on the right side of the paper, that's when you're going to get into the problem like this, okay? And let me tell you, so as I mentioned earlier, I'm trying to give you the whole overview to think about, okay, when you do a gas law problem, you're going to be deciding which equation am I going to use, in the future. Right now, it's easy because I'm doing the lesson, it's going to be PV and RT, but in the future, you might think it's this. Or could it be Dalton's law, So what you can do is when you read a problem and it seems like, before, this was the temperature and pressure, and then after, here's the temperature and pressure. Before and after is usually this kind of problem, PVT, PVT. However, in this problem, it talks about more gas is added, and there's a new pressure and a new temperature. So this is also a before and after, but it involves grams of the gas. So if it says something about grams or moles of gas, then this becomes a before and after PV and RT problem. Now, what I like to do, I like to actually derive the equation. Here's the way you can look at it. PV equals an RT. You can also say that PV divided by NT equals R. Now, I mentioned that in the last video, but then we didn't really need it then, and then didn't need to show that to the general. PV over NT is R. It's a constant. Okay, so that means PV, you can make, since it's constant, it stays the same. All right, so what that tells you is PV over NT, P1, V1, N1, T1 is equal to P2, V2 over N2, T2. Look at that. So we made a mega equation kind of like the other one you see there. Now, on this problem, let's just read what they give you here. It tells you have 2 grams of nitrogen gas. Okay, first of all, let's get that in moles. And we already did that in the other problem, didn't we? I erased my answer, but 2 grams of, it was 28.02. So it was 0.0714. So we know we have 0.0714 moles of N2. That's your N1, I'm going to call that. That's your initial moles was 0.0714. Is that right? 2 grams divided by 28.02. Yeah, 0.0714. That was your initial number of moles of gas. Okay, so you kind of think of this to the side here. Then it said that's how many moles you had at 25 and 3 atmospheres. So when the temperature one was 25, which we know is 298.2 Kelvin, because you got to Kelvinize it, and the pressure was, is it 3 atmospheres? Yeah. So sometimes you can just read every number and think that will be T1, that will be P1, and that has to be changed to moles. So we already did that on the earlier problem. I didn't write it down, but you'd have to change gram to mole. I would normally write it, but since we just did it on problem A and B. Okay. Now more gas is added, and the pressure goes to 5 atmospheres. Okay, so that means the new pressure, pressure 2, equals 5 atmospheres. And it says the temperature changes to 27 degrees Celsius. So 25 is 298. 2 plus 2 more is 300. That's going to be 300.2 Kelvin. Wow, all these numbers. What now? They want to know how many moles of nitrogen gas, what's the total number of moles that were in this cylinder. So that will be N2. So there it is. Now, notice they didn't give you one thing here. They didn't give you what? They didn't give you volume. Why is that? Because it's in a steel cylinder. And in a steel cylinder, a rigid container, the volume should not change. So if you wanted to, you can start. This is an equation that I like to tell people to, like for the AP exam, to memorize or to know that equation. They don't give you that equation, but it's true. In fact, if you really want to be technical about it, even this comes from that equation. You can take off the n's if the moles are constant, because in these, the amount of gas is constant. Then you get Charles Boyle-Gay-Lussac's law. But here, it puts together all of them together. All right, so the volume is constant. So the volume before and after stays the same. So that becomes true right there, that P1 over N1 times T1 will equal P2 over N2 times T2. So sometimes I do this a different way, just saying that I also, well, I don't want to confuse you with it. I've already shown you how. Just go with that one. But since I know the volume is constant, you could also say nRTV would equal, I am showing you to say I wasn't going to show you, but PV equals nRT, so V equals nRT over P. Okay, that will be true. If the volume's constant, then nRT equals nRT over P. N1, R1. Well, R won't be 1. It's the same thing, so that goes away. So N1 T1 over P1 equals N2 T2 over P2. Don't even look at that. Don't even worry about that. But if you wanted to kind of do it, that's how I used to do that. But it's the same. It should be the same thing. You should get the same deal there. P1 V1 over N1 T1. It's P2 V2. Okay, so pressure 1 is 3 atmospheres. I'm going to plug them in. I didn't need to tell you that part right there. 3 atmosphere. N1 is 0.0714 mole. T1 is 25 degrees Celsius. Oh, no. What am I crazy? See, I don't even do that. No, and there I never write it there, and that just stood out. 298 Kelvin equals P2, 3 atmospheres. Then over, we don't know the moles, the final moles, but we know the final temperature is 300.2 Kelvin. Well, Kelvin there. All right, so anything missed twice will get canceled. So Kelvin and Kelvin, atmosphere. When I rearrange it, it'll be moles. So I'll do cross multiplying to get it. 3 times N2 times 300.2 equals 0.0714 times 298.2 times 3. Okay. Hold on. That's wrong. 3. That's 5. Yeah, P2 is 5. Sorry. I noticed the same number there. So I know when I was doing it earlier, like, no, Vela, it was 5, Vela, what's going to happen to him? I wonder if somebody noticed that earlier. Okay. All right, so here's a cross multiplying step. So 300.2 times 3 is 900.6 N 2 equals, 0.0714 times 298.2 times 5. 106. I'll say 106. 3 sig figs. 106. So 900.6 N2 is 106. So divide both sides by the 900.6 so that you can get, well, actually that should just be 901, shouldn't I? Sig figs. I mean, you don't have to do sig figs till the very end, but I'll left it that way. I'll just put it that way. 900.6. Okay. So N2 equals 106 divided by 900.6. It's 0.117 moles. Okay, so notice you started at 0.0714 moles, but you ended up with 0.117 moles. That was number one. How many, what's the total number of moles inside the cylinder? You know what? There's one thing we did not ask here, and I'll add this on right here. How many moles were added? How many moles? It said some gas was added. Didn't tell you how many were added, because sometimes they ask that on AP. So when they say what was added, always know, okay, what were the moles before? 0.0714. Let me put it over here. So this is like a side thing that you need to know this though, how to do it. 0.0714. That was your, well, let me do it this way. I'm sorry. Final moles were 0.117 mole. The initial moles were 0.0714 moles. So when you subtract those two, you'll get that. So 0.046. When I use the little box rule, moles of N2 were added. I should have put that question in there. How many moles were added? So I put a 1, 2, and 3. I just put 1 and 2. I should have made another one. But okay, there it is. All right. Now, okay, the last question just says, how many grams of nitrogen? Oh, wait a minute. Ha! Well, on number 2, part 2, I kind of did ask that a little bit. Look what it says on part 2. How many grams of nitrogen gas were added into the cylinder? Guess what? That is part of part 2. Let me move on, though, and show you how to do it. Okay, the rest of it. How many grams were added? So, if we know that 0.046 moles, this is how you do number 2. So there it is. I didn't read ahead to see it. I was thinking, hey, we didn't ask that. But okay. That tells you how many moles were added by subtracting final minus initial moles. Change in moles could be delta N, if we call it that. Then how do I get grams of N2? Just change 0.046 moles of N2. Good gracious, it's chalk. Okay. Now I'm going to gramify it. Okay. That's not a word. Okay. Mole to gram of N2. My goodness. I just press it so hard that chalk is almost gone. I'll let you see how small it is. Okay. 1 mole of nitrogen, 28.02. I remember that earlier. Add 2 N's. So 28.02 times 0.046, 1.29 grams of nitrogen were added. A-D-D-E-D. Were added. Hey, I'll try to write that. Wow, that chalk's about to be gone. It's gone. Goodbye. Okay, 0.046. Yeah, 1.29. Okay, so anytime you see a before and after gas problem, before you had this many moles, this many grams, you need to see the picture better, get a picture or whatever. All right, this many moles, then after you had this many moles, etc. Okay, now, one more thing to show you, and this will be a little bit of a surprise. You're like, wait a minute, have I seen this before? Yes, you have. But since I don't have my notes in front of me, I'm going to probably have to do it again. Or I'll do it quick, but you can look back. Letter D, you have seen this already, and it says, chlorine gas is collected over water at a temperature of 25 degrees Celsius. All right, again, we did the same exact problem for Dalton, but I'm just adding on a little bit more questions with that. Okay, so, but look, right when I read that and I say chlorine gas is collected over water, I think, okay, the total pressure will equal the pressure of the chlorine gas plus the pressure of the water vapor above it. Remember, we talked about that. So immediately I made a custom equation for this problem. Chlorine gas collected over water, I know that. Temperature of 25 degrees Celsius, which is 298 Kelvin. We use that a lot because that's like a room temperature. 25. This time I just put 25 only on 2 sig. Well, we're going to keep it 2 sig figs. The vapor pressure of water is 23.77. I'll put VP 23.77 for H2O. And it says a total of 80 milliliters of gas is collected. volume is 80. I hope we get to go back and do this experiment. It's a fun experiment, and we've got some tubes that do this. Something, not chlorine gas. No, not with chlorine gas, but with a different gas. We get to do one. We don't use the yellow-green, poisonous, dangerous chlorine gas. Okay, water levels inside and outside are equal. As you'll see when we do that lab, the water levels have to be equal to really read the volume and to know when the pressure is equal as well. When the water levels are equal, that's when the pressure inside and outside are equal. Okay. The volume at which, yeah, well, you'll see. The volume, when the volume, never mind. You'll see it when you do it. When the water levels are equal in and out. You can look at that old diagram from the Dalton. Atmospheric pressure is 7065. So PATM, 765. I know some people don't like to make a list of all the units of all the data and then plug it in, but I don't always do that, but I'm doing it here on this problem. So the first thing, we already did this part. We know that 765.0 millimeters of mercury was your total pressure. We know that's true because the water levels were equal. Then we knew that the water pressure was 23.77 millimeters of mercury, and so we didn't know the chlorine gas. Did it say torr? Yeah, it did say torr, but remember, torr and millimeter of mercury are the same. You don't even have to show any math for that. So I'm going to subtract that from both sides. 765 minus 23.77, 741.23. 0.2, the sig figs. All right, that's the chlorine pressure, 741.2. Now, it says, what are the mole fractions for the gases in the flask after the reaction? And it says we already did that previously, and we did. I don't have it in front of me, of course. My chalkboard gets erased, but 741.2. The pressure of chlorine, we took the pressure divided by total pressure, 765. So what is that? 741.2 divided by 765. So 0.9689. Wow. Okay. And then for water, it would be 0.0311. The fraction of water. I just take 1 minus that number to get the water. Okay. All right. The work is already done earlier. All right. Then it says, okay, 3. How many moles of chlorine gas were collected? Okay. So, to do that part of the question, how many moles were collected, now you'll do PV equals nRT. Now, here's something interesting. In PV nRT, if I put in, I want to find the moles of chlorine. So I can say, okay, moles of chlorine can go here. And then I'd put here the pressure of chlorine, and I'll get out the moles of chlorine. Because the volumes are the same for everything. I mean, you could say pressure of chlorine, volume of chlorine. You could put chlorine there if you wanted to, but you wouldn't need to. They're all in the same volume. But pressure of chlorine. If I plug this in, and my volume and temp, I'm going to get the moles of chlorine. If I plug in my total pressure here, guess what? I'll get the total moles, all right? So this is a way, a kind of little short way to customize PV nRT. So I'll go back to this. If I put in the pressure of chlorine, I'll get moles of chlorine. So the pressure of chlorine was 741.2. The volume is 80 milliliters. I don't think, wait a minute, have I seen that before? Milliliter. Oh, you got to put it in liters, don't forget. So I'm going to draw it like that. Don't forget, and you can just do that little shortcut to go milliliter to liter. We don't know the moles, so we're trying to find that. The R is 0.0. Well, I guess I'm going to, okay, I can do it here. That's chlorine's mole fraction. I don't have to have this, I don't think, but I was going to just show you something that you don't need to worry about it really, but okay. 0.0821 liter atmosphere mole Kelvin to give me R. And then temperature was, what was it, 298? Yes, it was 298 Kelvin. Okay. 0.2 Kelvin. Okay. That's a 2 Kelvin there. Okay, now, again, back to my little cross-out stuff. So, even though it's messy, I can tell K and K cancel out. atmosphere, and oh my goodness, bad Vela. But you know what? It's good to catch myself on a mistake. Notice this. If you didn't put your units in, if I didn't, I wouldn't have noticed it. That's in millimeter mercury, and that one is atmosphere. Since, and I just erased it, but since I know that number, and they do give you this on the AP. If you, instead of liter atmosphere, if you would have liter millimeter mercury, the R value converts to 62.4. R is 62.4 liter millimeter mercury. Or you could change that into atmospheres also, if you wanted to. But I'm going to just leave it like this. So, hey, I caught a mistake, but see, it saved me. Because I couldn't cross out atmosphere millimeter mercury, but now I can because I know that I used the wrong R, okay? 62.4 is the R when you have liter millimeter mercury. Or if it's torr, they're the same number, 62.4. Okay, and that's the only two that they use on the AP. They don't use kilopascal. You might see it pop up even in the book, but they have not yet made a change to do that, and I won't get into why, but it has to do with physics people, and you know, there's always a war between physics and at the higher levels, the chemistry and physics always, you know. But I teach both, so I like it. I mean, I don't like kilopascal though. Okay, all right, here we go. Except, well, never mind, I won't tell you. Okay, all right. 741 times 80 divided by 1,000. Okay, that is 59.2930 equals 62.4 times 298.2, 18,608 N2. 18,608 N2. So let me double check this math. It looks kind of weird. 741.2 times 80 and divided by 1,000. That's correct. 62.4 times 298.2 equals 100 and... Yeah, that's right. 18,608. Okay, now I'll divide both sides by that. 18,608 to get this. So 59.30 divided by 18,608. It's a very small number. 0.003. Can I really have 4 sig figs? No, I can only have 3 sig figs because of that one. So I'll wait till the end and do it. If you use, even that one has 3 also. So 0.00319. Is that right? Yeah. 0.00319 moles equals N. 2. Moles of chlorine. Let's even be better. N of, I put N2. I'm sorry about that. N of chlorine. Moles of chlorine is 0.00312. Now, I don't think I really want to do this, but I was going to show you. Well, okay, I'll just tell it to you, but you don't have to do this. If for some reason, because sometimes like an AP question could be like A, B, C, D, E, and it might, this would be easy to do in this kind of problem. But if for some reason they ask you before this question, what were the total moles inside the container? If they ask you to find the total moles, I would put in the total pressure, which is 765. I would put in the total pressure here, but then I wouldn't get moles of chlorine, I'd get my total moles. Okay, once I have total moles, I could then, if I then say, well, how many moles of chlorine? How many moles of chlorine are there? I'll just take the mole fraction of chlorine times the total moles. 0.9689 times the total moles will give me that. So, oh well, there's no need to really, you can put that little step together in your mind. We kind of did that in the gas law part. Oh, let me see the last part. The last question says, what mass of chlorine? Oh, that's pretty easy. All right, so how many moles of chlorine? I'm glad I didn't completely erase it yet. You have 0.00319 moles of chlorine. So how many mass means how many grams of chlorine are there? So you could also write 3.19 times 10 to the negative 3. So go from mole to gram. And remember, 1 mole equals, chlorine on the periodic table is 35.45, okay? 35.45. But you have to double it, okay? So that's 70.90. Don't forget the Hofbrinkel. Okay, so 0.00319 times 70.90 gives you 0.226 grams of chlorine gas per in there. That nice yellow greenish chlorine gas. We'll never intentionally make that in a lab. Hopefully, I think what happens is sometimes in a lab, somebody might have cleaned out my labware one day and had some bleach in it. And some bleach might have been left in the container when they did a lab, and then you get the chlorine, the fun. Okay, we'll work those problems, and thanks so much, you guys.